Okay, we're going to look at part two now of using calculus in optimization problems. And I'm going to look at an example on page 246, example 31. So we've got an open box, like so, square based, x by x by h. So we're usually given zero information, except we have to be given some numerical information. And in this case, the surface area is 192 centimeters squared. And really important, let's go straight to what we're trying to find. Okay, so we've done 7x, and we looked at some examples here, didn't we? And we talked about it up here. We looked at always what's the target? What are we looking to do? Maximize area, and then get an expression in what we're trying to optimize. So we did a couple of examples in 7x, but so we're just extending a little bit here, probably looking at sort of perhaps more contextual questions, more maybe slightly more involved, might be slightly more difficult kind of differentiations we've got to do. But the concept, the principles are the same. We've got to maximum. What are we trying to do here? Let's look at the question. Maximum volume. So we want to maximize volume. Right, that is the aim of the question. That's the aim of this task. Aim, maximize volume. So what we're going to want to do here is get a little expression for volume. Now, at the moment it's x squared h, isn't it? Volume is x squared h. Now that's not going to work because we need this in one variable in order to do a div to something. So we need it in terms of x or h, but we can't have it in both. And so, all right, what we need to do is go back to what we've been given. We've been given that the surface area is 192. Surely we can use that, and indeed we can. So the surface area, we can write an expression for that, and that's x squared for the base. And then what do we got? We've got xh here, and we've got 1, 2, 3, we've got 4xh's, and it's open box. It's open at the top, so we're not going to include that. And that surface area is equal to 192. So what do you think we should do here? Get h in terms of x. That sounds sensible, doesn't it? So we could get 4xh equal to 192 minus x squared. And so then we can say that h is equal to 192 minus x squared over 4x. Okay, so that's what we're going to use for h, and that's what we're going to plug in here. So our volume is not going to read x squared h anymore. It's going to read x squared by this thing here, 192 minus x squared over 4x. We must be able to improve on that. We can remove an x there and remove an x there. So we'll get it back to, actually it might look better as 192x minus x cubed over 4, or in fact, to split that up, it's going to look better as 48x minus 1/4 x cubed, just so we've got it in differentiable form. So that's my volume. Now remember, our aim is to maximize volume. Anything we want to optimize, we're going to have to get the derivative for and make it equal to 0. So we're going to get div dx here. We want to get the optimal value of this. Div dx is 48 minus 3/4 x squared. That looks fair enough. Make that equal to 0 to find out the optimal value. So, right, let's solve this thing. So therefore, 3/4 x squared equals 48. Away we go. X squared, now we're going to divide by 3/4 or multiply by 4/3, aren't we? So 1 3 there, 16 3s there. So we've got x squared equals 16 4s are 64. So therefore, x is equal to plus or minus 8. Now while we're in this algebra phase of the question, we've got to represent all our solutions. So x squared equals 64. I'm not going to dump minus 8 yet. Clearly it's ridiculous to involve minus 8 in this discussion because x is a length, but I've got to write out my algebraic solutions in full. I can then therefore say I can discard x equals minus 8, x equals minus 8, alright, as x equals a length. Alright, stating the obvious, but sometimes it's a good thing to do. So therefore, x equals 8 is where my first derivative equals 0. What I need to do now is I need to verify that I've got a maximum at that point. So I'm going to find d2v dx2, which is minus, this 2 comes down, so it's minus 3/2 by x. Alright, now what's that equal to when x equals 8? Minus 3 over 2 times 8, which equals, doesn't really matter, it's minus 24 over 12, it just matters the sign, it's negative. Negative 12, therefore, concave down, therefore, right, we've got this sort of shape, haven't we? So therefore, we've got a relative or a local max at x equals 4. Okay, so at x equals 4, we've got a relative max. That's brilliant. Sorry, not at x equals 4. I'm talking about x equals 8. At x equals 8. But let's go back and make sure we answer the question. It says, find the dimensions of an open box that has a maximum value. So therefore, so we need to answer the questions. So the question, therefore, dimensions which deliver a maximum volume are x equals 4, h equals, now what's h equal to? Got to put it in here, 192 minus 16, 192 minus 16 over 16. So 192 minus 16 is 176. 176 over 16, that's 11, I believe. So we've got a height of 11. Okay, I just realised I've botched that up. Apologies for that. Again, I don't know why this obsession with x equals 4. That's not correct. So so I need to put in here. Again, I've written it there, haven't I? X equals 4. What's my issue? X equals 8 dimensions, which deliver a maximum volume where x equals 8. H equals 192 minus 64 for h squared over 32 for 4x. 192 minus 64, that's 128 over 32, which is 4. So finally I have got a 4. So x equals 8 and h equals 4 are the dimensions that deliver a maximum volume. We've solved the problem. Excellent. Last exercise, 7y, and we'll attack that with great enthusiasm on Thursday when I see you next. See you then.